then you can start.
Okay. Hi, we're Group 3 with Aerospace Design 1 presenting Project MMXL, which is the Martian Moon Exploration Lander. Our group consists of Aaron, Alina, Colin, Jonathan, Jose, Natalia, and Nathan. Our mission objective is to return 50 kilograms of lunar samples from each of the Martian moons, as well as scientific data and photographs from those moons to better understand their origins and the evolution of the early solar system. Our budget for this mission is $1 billion. It will be completed with a crew of 2 astronauts. Our vehicle will launch from Earth on August 15th, 2037. And will begin its mission on January 1st, 2040, after the crew arrive in Martian orbit on a deep space transport. The mission must be complete by January 31st, 2040. So here's a little bit of our concept of operations. We'll launch from Earth on August 15th, and then we'll spend a week in orbit, checking our systems and refueling the Starship to continue to Mars. We'll boost towards Mars and then separate from the launch vehicle starting on August 22nd. We'll arrive at Mars in a 5-sol parking orbit on March 30th, 2038, where we will wait until January 1st, 2040 to dock with the deep space transport and transfer the crew. On January 3rd, we'll descend to Phobos and enter its orbit before landing the next day and releasing our robots for sample collection. Sample collection will take approximately a week before we leave Phobos and arrive at Deimos on January 13th, 2040. We'll enter orbit before landing the next day. On January 14th, we will release our other set of sample collection robots. Again, collect samples for approximately a week. We'll leave Deimos on January 22nd, 2040. And arrive back at the deep space transport to transfer our samples and crew back to that vehicle on January 23rd, 2040. So now I'm going to discuss our launch. We compared every heavy lift launch vehicle currently in the market or expected to be operational by 2035. And we found that Starship in an expendable configuration gives us the best performance at a reasonable cost that meets our budget. Our Starship is expected to first fly in 2025, and this will be plenty of time for it to be fully developed by the time our launch is. So our launch vehicle, like I said, is SpaceX's Starship vehicle. We expect it can carry up to 150 metric tons of spaceship to Mars, and we'll be able to refuel in orbit to enable that. It will boost the EEV to Mars transfer orbit, and additionally, it has a payload volume of 1,100 cubic meters, which is the largest of any spacecraft.
All right, so I'm Nathan. I'll talk about our trajectories and landings. Next slide, please. So we evaluated launch windows in 2037 and 2039, but found that the 2039 transfer window does not get us to Mars on time. So after many iterations of trajectory analysis, we chose an Earth departure date of August 22nd, 2037. This trip will take 220 days with an expected arrival of March 30th, 2038. Next slide. So that day, the Mars insertion burn will occur as in the video. This breaks from interplanetary velocity into an orbit with a period of 5 Martian days. But since it will not initially be equatorial, after checkouts are finished, an inclination change burn can occur at any ascending or descending node in the orbit. Then we will be in our final parking orbit waiting for the DST. Next slide. We did a trade study on which trajectory would be best for visiting the Martian moons. We found that performing one voyage to both the moons was faster and cheaper than doing 2 sorties, one to each moon individually. Then we decided that visiting Phobos first would be the best because it is a more interesting target scientifically. And if we had to abort the mission at any point, we would like to maximize the chances that we had collected science on Phobos first. Next slide, please. As for operations around the moons, we found that Keplerian ideal orbits wouldn't work because of the moon's low relative mass to Mars. So we investigated some NASA research and found that using three-body orbital mechanics, we could go into several different orbits. The one we chose is the distant retrograde orbit, which is a stable and cheap way to orbit the moons before landing. The other orbits shown are unstable over time, but each have possible uses for scoping out landing sites prior to landing. Next slide. Now, by searching the literature and verifying with STK, we determined several regions for landing, or we evaluated several regions for landing. The North Pole near Grilded Crater on Phobos is the best location on Phobos, and the North Pole on Deimos is the best on Deimos for maximizing sunlight, which is important for the EEV's electrical and thermal systems. So those will be our landing locations. Next slide.
Okay, I'll be talking about propulsion design, and then Nathan will finish it up. All right, so for picking our propellant, we first considered our RCS propellant. We considered monopropellant and hypergolic bipropellant. We went with the latter due to its much higher ISP. As for the propellant for the main engines, we considered a few other options, including cryogenic bipropellants and ion propulsion. On the right, you can see the estimated mass ratio and the dry mass limit based on the our wet mass limit due to Starship's launch capabilities. We ended up choosing hypergolic bipropellant. This is primarily due to the fact that it allows us to use the same fuel as our RCS, which simplifies our propulsion system significantly, and is much easier to store the propellants over time than it is a cryogenic bipropellant. Additionally, the ion propulsion, while it has great ISP, was just too low of a thrust for our burns. Finally, the bipropellant specifically we chose was nitrogen tetroxide and monomethyl hydrazine, as this is widely used in a variety of engines. Some other ones that were looked at are listed here, and as you can see, were used either in older engines or not in America. Now for the engines themselves, we looked at a few options for the main engine. They're listed here. We ended up choosing the Orion main engine. This is a improvement over the shuttle's orbital maneuvering system being created by Aerojet Rocketdyne. It's currently in development, so we don't know the exact specifics, but we know that it is better than the OMS. So the 3/16 seconds there you see is the OMS's ISP, so we know it's an improvement of that. The other two engines were rejected due to the literature I saw, seeing that they had limited restarts, and for us it was not enough restarts for our mission. For the RCS engines, we chose the R4011, primarily due to its extremely flight-proven qualities. It was qualified for 31,950 restarts, compared to the other engines, which were only qualified for a few hundred. So in summary, we're using nitrogen tetroxide and monomethyl hydrazine. This is a 1.65 to 1 oxidizer to fuel mass ratio. We're using 3 of the Orion main engines. Each of these has 33 kilonewtons. Based on our delta V we needed, we calculated that the amount of thrust, our minimum desired thrust would be 90 kilonewtons because we wanted our insertion burn to be less than 30 minutes. As for the RCS, we're using 24 of the R4011s, and that number was again arrived at based on a moment we calculated for how quickly we could turn. So we calculated a 10 kilonewton meter moment, and using 24 of these gives us at least that in all axes of rotation. And additionally, both these engines are used in Orion, which means they will be in production at the time of our mission. Okay, for the fuel tanks, we're using a metal bellows tank design. This allows the tank to resize as the propellant is used, maintaining the propellant pressure to the engines as all the engines are pressure fed. And additionally, this separates the pressure from the propellant, so there's no chance of the helium pressure entering the engines.
All right, so we did a trade study on staging options for the most efficient way to break into Mars orbit. The single stage option assessed would use the EEV's fuel for all the maneuvers, whereas we evaluated a triple configuration of solid motors for the multi-stage option, particularly that because long duration commercial liquid upper stages hardly exist now or in the future. So we found that the single stage option still outperformed the multi-stage option in both mass and risk. So we go with the single stage option for the EEV. Next slide.
So I'm Colin. I'm going to be discussing our structure design. So when looking at how to build our structure, we looked at 3 standard aerospace structure types. And we ended up selecting the skin stringer type because its versatility was significantly higher than some of the others, which will allow us to easily mount the equipment that we need on our spacecraft. We're also not extremely concerned with minimizing weight, and so this increased versatility was determined to be an improvement that outweighed the weight penalty for a skin stringer configuration. When designing our structure, we looked at 4 different common structural metals, and we selected 7075 T6 aluminum due to its high strength to density ratio and low relative cost. Some of the failure modes in our structure are buckling during launch when we're experiencing 4.5 Gs of acceleration. Under this condition, we have a 1.51 factor of safety for our longerons. During pressurization, which is pretty much the entire time that the mission is ongoing, we have a factor of safety of 1.51 on our skin and on our longerons, as well as our ring frames. Additionally, when we are making maneuvers, we have a factor of safety of 1.59 on our engine mounts. So here's an overview of our structural design. You can see the kind of gray outline is Starship's cargo fairing. So our ship has a diameter of 6.5 meters with a height of 16.4 meters. This only fits on the Starship vehicle, which is 8 meters in diameter and 17.2 meters tall. Kind of as a sense of scale, each of the square panels you can see on the lower portion of the vehicle are approximately 1 square meter.
So we assessed many landing modes. The first was simply hovering with our RCS fuel versus using legs with either pyrotechnic drilling or melting anchors. And lastly, we evaluated widely stanced legs with no anchors. Hovering required too much fuel and anchors added complexity, but with the high mass of the EEV, using legs with a very wide stance is very stable against perturbations even without anchors. So we chose widely stanced legs with no anchors. They are 10 meters long and have a factor of safety of about 2. Next slide.
Okay, I'll be starting discussing sensors, and Jose will discuss telecommunications. So as for our sensors, we're using star-sun trackers to determine our orientation in space, with a ring laser gyroscope to determine orientation when the star and sun are blocked, such as when landing on the moon. For acceleration, we're using an IMU to measure that. For our computers, we're using multiple computers with what's called software radiation hardening. And essentially, this means that the redundancy is handled via software instead of just trying to reduce the effect that the radiation has on the computer via hardware. This is less expensive than hardening the hardening, and is recently proven to be effective based on experiments on the ISS.
All right, so our telecommunication system design consisted of first assessing the transmission needs for the EEV, which we have here on the table to the left, which is approximately 10 megabits per second, taking into account all of the different functions. So we consider the options of using a laser-based and a radio frequency communication system. And so each with a theoretical design of 10 megabits per second, we found that the laser-based communication system outperformed the radio frequency one in power, mass, and cost, with the complexity of each taken to be approximately the same. This is why a laser-based communication system was chosen as the primary method of communication with a radio frequency system as a backup. Next slide. So our laser communication system is adapted from already existing NASA systems undergoing testing and development. To best implement the technology into deep space, we chose a system with two 10-centimeter lightweight glass reflective telescopes, each equipped with a protective membrane to reject solar radiation. The signal is modulated in pulses with pulse position monitoring modulation. And at this time, the system is capable of a minimum of 10,000 kilobits per second of data rate transmission, with future research and development supporting even higher reliability and data rate capabilities. Next slide. Our antenna system is equipped with a high gain antenna and a low gain antenna. The high gain antenna has a parabolic dish with an ellipsoidal subreflector for very precise pointing and high data rate capabilities, and it operates at K-band and X-band. We also have two low gain antennas, one each for receiving and transmitting in cases where we cannot accurately point towards Earth with the high gain antenna. The antenna amplifier enclosure is also attached to a gimbal mechanism and a rotating motor boom to give it the ability to point itself towards Earth independent of the orientation of the spacecraft. The system is capable of 7,500 kilobits per second, which would support the basic mission needs. Next slide. Now I'll be covering our scientific objectives and the equipment we use to achieve these. Next slide. One of our most important objectives is to discover the moon's origins, which we plan to accomplish through these several objectives. This includes assessing the geological history and associated environmental history, characterizing the overall landscape geomorphology, observing the terrain disturbance, and providing hedgehog operational support. Next slide. So to accomplish these tasks, we went with 4 pieces of equipment. This includes a neutron spectrometer that shoots helium-3 at the moon's surface and detects the hydrogen abundances, which can be indicative of water traces. We also implemented the Mastcam-Z to take high-resolution images and video with a powerful zoom function, used for monitoring and observing the surface interactions and sample collection. Next slide. Our next equipment is a LiDAR moon mapping system that computes the distance between the light pulse emitter and the surface to provide high-resolution topographical information in ranges from 7 kilometers to 10 meters from the moon's surface. And finally, we also went with a ground-penetrating radar system to image different ground densities and structural layers up to 10 meters deep in the surface, depending on what the subsurface looks like. This system also detects the reflected radio frequency waves as a function of time. Next slide.
Hello, I'm Aaron. I'll be talking about the life support system of the EEV. Next slide. So first, food will all be freeze-dried food, which helps keep the food from spoiling during the mission. The EEV will install a storage containing 150 kilogram of food for the 2 crew members. Water tanks like those used in the Space Shuttle Endeavour will be used for the short duration mission. So a total of 270 kilograms of water will be required for the duration of the mission. Therefore, we will provide 4 water tanks, each holding 75 kilograms of water, giving us a total of 300 kilograms of water. Next slide. For oxygen supply, we decided to use the Vika oxygen system. The canister contains lithium perchlorate and produces lithium chloride and oxygen when burned. So we'll need about 50.4 kilograms of oxygen for the 2 crew members, and 1 canister can produce 0.6 kilograms of of oxygen. So in total, we'll need 84 Vika canisters. Next slide. So we decided to use the carbon dioxide removal assembly, CDRA. The EEV should be kept below 4 torr of CO2 for safety, and the CDRA can maintain the cabin at less than 5.3 torr of CO2 for 9 members in the ISS. So therefore we'll be utilizing less power since the EEV will only have 2 crew members. Next. And lastly, for waste management, we decided to install the universal waste management system, which is fairly a new system created. It gives easier cleanup for the 2 crew members, and we'll be using containers for liquid waste and then micro perforated bags for solid waste. We decided that all subsystems for the life support system will be an open loop system instead of a closed loop like the one at ACLSS, because it's only a 30-day, it's a short duration mission, and it'll cost way less. Next slide.
So this is kind of a visualization of what we're thinking for our crew habitat. Our total pressurized volume is 165.4 cubic meters, but the open area is closer to 127.2 cubic meters. This is still the most spacious habitat in space, and it beats the ISS even by 5% on a volume per astronaut basis. Our crew habitat will include areas for rest, exercise, relaxation, eating, and scientific research. And one possible configuration of this space is seen in the image on the right. Now, to protect our astronauts against radiation, we looked at the wall materials we could use. We found that high molecular weight polyethylene can most effectively protect the crew from radiation while also being very easy to use and inexpensive, as well as being a good thermal insulator. The astronauts will bring their AstroRad radiation vests from the DST. And this combined with high molecular weight polyethylene at 25 millimeter thickness in our walls will lead to a 50% reduction in the radiation that they are exposed to. We determined that overall this gives them only a 1.25% chance of exceeding NASA's limits for astronaut exposure. Now I'm going to discuss our thermal and power systems. Our thermal requirements are that we must be able to continuously get rid of 1,723 watts of thermal load. And at a peak load, we'll need to eliminate 4,092 watts. This is primarily due to the high levels of heat produced by the oxygen generation system. We want to be able to maintain our crew temperature between 72 and 78 degrees Fahrenheit. And we also need to maintain our fuel temperature between 13 degrees Fahrenheit and 70 degrees Fahrenheit. We looked at 3 different methods for heat transmission, and we determined that a pumped fluid system is the most efficient. Although it isn't the most efficient in terms of weight, it is the most efficient in terms of power. In addition, it also provides additional radiation protection for our astronauts. So here is kind of a cutaway of our walls. You can see the radiation insulation in our high molecular weight polyethylene, as well as the tubes that our pumped ethylene glycol and water mixture will be pumped through. We will be painting the dark faces that aren't facing the sun with Vantablack while maintaining bare aluminum on the lit faces, which allows us to release up to 16,703 watts and absorb up to 11,084 watts of energy from the surroundings. We have 4 pumps for redundancy, as well as to prevent freezing and evaporation. We can vary the flow rates throughout the walls to make sure that we are releasing and absorbing the correct amount of energy at any given time to maintain the fuel and crew temperature. Now our power budget, we have a base load of 1,723 watts, as well as a 15-minute peak load of 2,558 watts. We found that a combination of solar panels and batteries can produce energy at 13 watts per kilogram with a very high level of safety and a low complexity. So we plan on using 28% efficient deployable solar panels on Northrop Grumman's Ultraflex arrays. These will be 1 kilowatt arrays. We'll have 2 of them, and they'll be approximately 3 meters in diameter. We will also be storing 12 kilowatt hours of energy on 770 cells that are in the 21700 shape.
Hi, I'm Natalia, and alongside Alina, we're going to talk about sample collection and containment. Next slide. So many sample collection methods were evaluated for this mission. One of the biggest challenges that we face is the gravity on the moons. The force of gravity on Phobos is only 0.05% the gravity on Earth, and it's even less on Deimos. We evaluated 5 sampling methods: a coring drill, the touch and go sample acquisition method, a pressurized gas tube called Planet Back, a traditional rover, and hedgehog rovers. So the first 3 methods, they would be attached to the EV itself. These methods either required anchoring the EV to the ground or multiple landings on the moon, which would require a lot of fuel. Additionally, These methods would make collecting the minimum 50 kilogram samples per moon in a timely manner very difficult. A separate rover would allow sample collection from various areas of the moons without the EV having to actually move to those multiple locations. A traditional rover like Perseverance is highly developed technology and proven to be successful. However, Perseverance, for example, weighs over 2,000 pounds on Earth, and on Phobos, it would only weigh a little over a pound. There would be no traction between the wheels and the ground, and if there was a small perturbation, the rover could topple itself and not have a way to right itself. Next slide. So this is a visual of what would happen to a rover like Perseverance on one of these moons. It would just fly off and we could possibly lose it. Next slide. So this leads us to the sampling method we chose, which is the Hedgehog rovers. These robots are designed by Stanford and JPL specifically for low gravity environments. They are cube-shaped robots with 3 orthogonal internal flywheels attached to motors. And when a brake is applied to a spinning wheel, this generates an impulse which can move the rover in a specific manner or direction. Next slide. So this is a rolling maneuver. This is the rover in a microgravity environment. This is what rolling would look like. Next slide. And then this is a hopping maneuver. Next slide. Now the Stanford and JPL design is not designed to collect samples, so we modified a design to have a tray of 16 test tubes open to the environment. These test tubes would face down towards the ground, and when the Hedgehog performs a spin maneuver around the z-axis, such as in the video on the slide, material is kicked upwards towards the test tubes. The test tubes would then be closed, trapping the material inside, and the Hedgehog would then return to the EV. This mission would have a total of 10 Hedgehogs, 5 for each moon to prevent cross-contamination. And in order to collect the 50 kilograms of samples, we made a very conservative assumption that only 10% of the total volume of a test tube tray would be filled during a single collection. Using this assumption, we calculated that we would need 30 trays to collect 50 kilograms. Therefore, we would need a total of 60 trays for the entire mission. Next slide. Alita, you're muted.
Sorry, 2 robotic arms will be attached to the EEV and will be utilized to transfer the sample trays into it and replace with new sample trays. This will occur a total of 30 times on each of the moons. The robotic arm has a full command to the gripper to open and close it, a wrist motion of 180 degrees, an extensive elbow range base motion, and a vertical and horizontal reach of 6 meters. This allows for a very easy transfer into the EEV. Next slide. When the robotic arm inserts the sample trays into the EEV, they are slowly pushed through a barrier of Kevlar, which deforms to envelope the sample container. This membrane around the sample tray is heat treated during this process and pinched by the robotic arm to seal the sample tray from any sort of contamination. Kevlar is a heat-resistant and strong synthetic fiber that can easily be deformed and reformed. Its properties are comparable to Nomex. Inside the EEV, the robotic mechanism then places these sample trays after its cross-contamination process in a 1.5 meter cubed configuration, which will be easily transferable between the EEV and the DST. Next slide. I'm now going to speak on the cost and mass budget. The cost for the mission was estimated to be around $438 million based on 2021 cost estimations. Utilizing SpaceX's Starship, which contributes the most to this budget analysis with a value of $250 million, followed by the scientific equipment with a value of $80 million. Next slide. Utilizing SpaceX's Starship in an expendable manner, it was found to have an estimated payload mass of 150,000 kilograms. This mass value meets the needs for our MMXL mission, which has a wet mass value of 129,441 kilograms and a dry mass value of 22,641 kilograms. The largest contribution to the dry mass budget is from the structure, followed by the propulsion system.
All right, any questions?
Right on time. Thank you for the presentation. So any question from our audience?
Hi guys, this is Tom Singer from Northrop Grumman. You mentioned that you're planning on a 23-day total mission length.
Yes, I believe so. Let me, sorry, I might close the screen share. Let me share here. I believe that's correct.
What's driving that time? Is it mostly transit time? Is it time to do scientific operations on the surface, or what's driving that?
Yeah, so about 2/3 of that is spent collecting samples, and that's primarily just to ensure that we can collect the amount of samples that we want to. We calculated that we could probably do it in about 36 hours per moon, but because this is kind of an untested technology as of yet, we wanted to make sure we have a full week on each moon. This gives us, the astronauts, additional time to do their own scientific research as well.
Mm-hmm. All right, so there's some margin sort of built into that based on what you think it'll actually take to collect 50 kilograms of samples.
Yes.
Yeah, I like the hedgehog. I know in other classes, Dr. Traum is always talking about hedgehog concepts, and here we actually have a hedgehog concept, so I appreciate that. The method of locomotion is really cool, but I wonder if it seems like it's going to launch itself off into orbit, right? I mean, especially on Deimos, the gravitational field is so weak. It doesn't seem like it would take much to kick a body way off the surface, and maybe you can scale those reaction wheels down and do things with that. But it seems like they're potentially just gonna hop off and be unrecoverable. But I do like the idea. I question how long it'll take to collect 50 kilograms of dirt. And I especially question, what do you do if the surface is kind of crusty? But it is a cool concept.
Yeah, I mean, there are a lot of unknowns both about the moon and about this. So, you know, we definitely hope it's kind of a powdery, easy to kick up some dust, but they also do have the ability to maneuver. And we do think that, you know, we can control them fairly accurately. Just, you know, applying more or less torque depending on what moon we're on, for instance. So yeah, definitely a lot more testing would need to go into this to verify it for sure. But
yeah, I believe our assumption of the sort of loose regolith is based off of knowledge of other similar sized space bodies, like large asteroids, where we've discovered recently that it's just a bunch of loose particles.
Okay, Dan Plawecki, also from Northrop Grumman. Could you flip to slide number 45?
Yep.
So the glycol water mixture flows through the void there in the wall. It seems like it's a very thin surface before you get to occupied space. If you incur damage and you begin to leak glycol water into the occupied space, so how do you control that?
So the surface that you can kind of see here is actually open to the atmosphere, or not the atmosphere, to space.
Okay.
So if there's any leakage, it would be out into space. Because we're using 4 pumps, we can kind of control. We have, I think there are solenoids connected to each kind of wall section. So we can easily turn on or turn off. We can redirect the flow wherever it needs to go, turn off specific panels. But we're also not deploying the EEV until we're out of low Earth orbit. So we're not as concerned with some of the space debris that's in low Earth orbit. However, we can shut off some panels if we experience some leakage of that nature.
Okay, so they're isolated. You could isolate the panels so that if you incur damage in any one of them, you would isolate it, and you'd have to deal with the degradation as a result of that, right?
Right. Yep. And we have 180 panels total, and we can release approximately 4 times as much power or thermal energy as we expect to produce. So we definitely have some margin there.
Okay. Perfect, thank you.
Yep.
Oh, Dr. Trom's got a question in chat.
Let's see.
Yeah, I can. I didn't want to interrupt Dan, and I also didn't want to lose my thought. But with respect to the collection technique, I think I heard you're imagining or assuming a 10% fill of the test tubes, and it just occurred to me, what if the process is quite a bit more efficient rather than less efficient? And if it's quite a bit more efficient, you've now got 450 extra kilograms of stuff on, I'm not sure how heavy the spacecraft is, but all of a sudden that changes all of your orbital mechanics, right? So what if you collected way too much stuff? Is there a plan for that? Can you still get your spacecraft back to the mothership?
So because each of the trays are removed after they're like continually being removed, we could, when they're being, when the tray is brought onto the EV, we could measure how much samples were collected at that time. And then if we reach, our minimum 50 kilograms, before we end up using all the trays, we could probably just stop collecting and not need to further collect additional mass that's not necessary, since we're like constantly receiving the trays and not just sending them all out at once.
Yeah. So how do you measure the mass? Sorry, I'll turn my camera on here. How do you measure the mass of the stuff you've collected?
Since when we bring the trays onto the EV and they're being put through the sample containment, the assembly with the Kevlar, like as they're being passed through, we could just measure the mass as it's being brought through.
Okay, I'm still not fine. Granted, the last time I did aerospace engineering was 2003, but you're in like a microgravity environment, right? So how I'm still not sure how you measure the mass. You spin it, is what Tom is suggesting.
Yeah, from my understanding, I don't think we've discussed that too much of, measuring that specifically. I think that, there's be some way of, apply a force, see what happened, and, then you can figure out your mass. But we haven't really discussed that until this point. So that's definitely a good thing that we would need to keep in mind.
Yeah. Okay. Just checking. That's the first time I've asked an aero question. Yay. Thanks.
While we're talking about massive stuff, you said you were carrying 300 kilograms of water, which works out to 80 gallons or so. So for 2 people over a 23-day mission, that's about 2 gallons of water being consumed per person and not being able to be reused. Did you consider any sort of water recycling? What was the trade there?
Yeah, so we considered using the ECLSS at first, which has like all like this recycling of like water and then recycling of like carbon dioxide and stuff like that. But I think just because like the mission is for 30 days, then we just stick with like I said, like an open loop system, because it'll cost more, and also like, and we won't need to have like as much mass as we will need if we use the ECLSS.
If I remember correctly, it was like the mass of the recycling system, in addition to the extra power and batteries you would need to power that, because it's also very power intensive. But the overall mass that it would add was, I think, either more or comparable to just having that water, the extra water.
And in addition to that, we'll need that means we'll have to use more power as well, since those kind of system will use power instead of this one. It's just like,
yeah. Are you taking advantage of the water for like radiation shielding?
We're not. That that could be a side effect. Our let's see, where is it? I'm trying to find the slide that kind of shows the configuration of the, oh, here it is. So our water, is kind of going to be stored around, as well as our Vika canisters are going to be around this top area. That's kind of our current plan, but we're not, we're not planning on using that primarily for radiation protection. We reached out to AstroRad, which is the company that makes these vests that are used on the DST. And they said that combined with, the layers of high molecular weight polyethylene would provide about a 50% reduction in natural exposure. Additionally, we're pretty far out from 2040 right now, and solar cycles are not very predictable. So as we would get closer to the mission time, we would be able to see whether our expected chance of excessive exposure would increase or decrease, just depending on how long the current solar cycle is and how long the next solar cycle is. So a lot of unknowns there just because of time. I mean, they'll be 7 years long and then 13 years long and then 11, and you just never know. But we think that the thermal fluid pumped through the walls, in addition to the plastic and these vests, should be sufficient.
I would suggest anytime that you can take advantage of a material for multiple uses, it's probably a good idea, particularly when you are as concerned about mass as you are in a spacecraft. So that might be an opportunity to tweak your design a little bit. If you're going to do that and you're talking about consuming water, instead of putting it in bags, you may want to pump it back into your tanks with some sort of barrier between sort of the clean water and the gray water. But yeah, I think that's maybe something to consider there.
Yeah, I mean, we could definitely rearrange our habitat to provide more protection, especially during sleeping. Yeah.
And you said a 1.25% chance of excessive exposure. Is that if there is an emergency, a coronal mass ejection or something, do you have some sort of contingency plan? Do they have like 4 more vests they can put on, or what's kind of the contingency there?
Yeah, so this is based on, if there was no solar particle events or anything like that, there'd be virtually no chance. So this is almost entirely based on those events, and they wouldn't need to wear the vests if there wasn't an event ongoing. One concern with that is that those events hit the spacecraft pretty quickly, so they're going to be kind of rushing to get the vest on.
Well, do they though? I mean, my understanding is like a coronal mass event to like Earth vicinity is on the order of what, like a day?
Okay. Yeah,
So
when
like,
I was looking into it sounded like
I mean, it's certainly an emergency situation where you have to react to it. You don't have time to get back to some other protective configuration, but I think you certainly have time to say, hey, let's move some mass over here. This part of the spacecraft's facing the sun, and then we'll huddle back down here.
Okay.
It may require reorienting your spacecraft, but I think, as sort of an emergency procedure, I think that's pretty feasible.
Yeah, I mean, there's when I was looking into it, it sounded like we would only have about 1 to 2 hours. So that's kind of why I was, like, okay, do what we can, but there's not a ton that we can do. We can't get to a different place in orbit or anything like that. If it is a longer time frame, then it's possible we would be able to move to a different part of the moon, one that would be a little bit more protected. And we do have the propellant and energy factors of safety to be able to do something like that.
All right, and speaking of propellant, one more question. So you were entering Mars orbit at a pretty high inclination. Is there a reason for that?
Yeah, I can talk about that. So from the trajectory analysis, essentially the high inclination is just a byproduct of the most efficient of the most efficient transfer orbit.
Mhm.
So it was difficult to avoid a high inclination entry. That's, I believe, around a 40-ish degree inclination, but also because we're so high off the surface, it's not as expensive as it would be close to the surface.
To lower the inclination?
Right.
Okay. Yeah, I mean, it seems for a transfer orbit, it seems like a real minor change in velocity is gonna like put you down on a lower inclination orbit as you enter. And if that's not the most efficient transfer orbit, it feels like it would be very, very close to your optimum. But if as you say, there's not a lot of delta V cost in lowering that inclination, maybe it's not such a big deal. But it strikes me as surprising.
Yes, like perhaps there's more trajectory analysis. Like I did a lot of trajectory analysis to get to this point, but perhaps like with further trajectory analysis or better simulations, there could be a different trajectory found that results in a lower inclination change. That would be what I would pitch for like future work. And I was trying to think, there was something else I wanted to mention about this. Oh, also a lot of spacecraft entering Mars can take advantage, like if they're trying to land on Mars, they might take advantage of you know, entering the atmosphere for their braking so they don't have to use fuel, and then they're not concerned with an inclination change necessarily. But that was one of the trade-offs here with entering orbit versus landing.
Yeah. Okay.
Thank you.
Thank you, guys. I'm gonna jump off and grab the next presentation. Good job.
Thank you.
Thank you.
Are there any other questions?
Any questions?
No, but I want to say good work on everything, guys. This is a very thorough presentation. You guys have come a long way this semester and learned a lot about this process and everything. So congratulations on getting it all done.
Thank you.
Thank you.
Thank you.
Thank you.
Any question from our audience? Or are there any? So since I was in your rehearsal 2 days ago, so I don't have too much to comment. And I'm just curious. There are several things I may want to have some clarification. So on page 16. Okay. So the thrust of each main engine is 33.
Yes.
And you have 3 engines?
Yes.
Okay. Okay. So minimum required you calculate is 90.
Yeah. I couldn't fit the whole thing in there, but essentially we calculate the minimum thrust based on how like the insertion burn, since that was our largest burn. We didn't want that to exceed about 30 minutes. Because the longer it goes, less efficient it is, and so 90 kilonewtons of thrust ended up being about that 30-minute threshold, and so with using the Orion manage, that means we need 3 of those.
Okay. Okay. Great.
And then for the RCS, it's the same thing. We calculated, you know, the moment needed to turn at a specific rate based on looking at other spacecraft's turn rates. Yeah.
Okay. Great. That's great update on the size, on the information and everything. Thank you. And on page 22.
Yep.
So you did the buckling analysis, the pressurization situation, and also the bending caused by engine. And you have the safety factor 1.551, 1.51 for both the buckling and pressurization situation. it just a little surprise to me. It's like, wow, it's
Yeah.
happening.
Yeah, no, it was surprising to me too, but I went through and that pressurization is primarily the stress on the outer skin, but I went in and did the whole Moore circle analysis and divided, and yeah, 1.51. I was like, wow, okay.
Yay.
Yep.
Okay, so what is the size you use for this kind of calculation? Like what is the thickness of the structure, and you get a conclusion the safety factor is 1.51.
What for the buckling or?
Well, it should use the same thickness of the structure for all the structure analysis, right? And then you have the safety factor. So what kind of thickness you used?
So I mean, this was based on the buckling of our longerons. So they're going to experience, it's only a 1 meter section at the bottom that experiences the highest stress, since as you go up, there's less and less mounted to it. So this is also bolted to the sheet metal. And so the sheet metal of the walls is an additional 3 millimeters. So I kind of just extended this face by 3 millimeters when finding out the moment of inertia. I didn't include the whole sheet all the way, because that's not super precise, but I can get the exact area for you if you want.
Yeah, I probably will check more detailed information in your final report. I just want to know more about the actual structure analysis and everything.
Right.
Structure analysis.
Yeah, I mean, I have it written in the report somewhere down here, but yeah, I can't pull it up right now. But it's, I went through and there are equations in the report as well as the numbers that we used for all of that.
Okay, so I think that's all the question I have. So overall, great job. This presentation, I think, and also, I think your group has a lot of creative, like the sample connection and the thermal control and everything. So, and the presentation overall and amount of work done, I think it's like much higher level than the PDR. So congratulations, and work hard on your final report. I'm expecting to read more detailed information from your final report and send me the recording.
Okay.
Yeah.
Yep.
Thank you.